Okay, so this is lesson 12, which is chapter 18 in your textbook, and it's all about metals. And in a way, it finishes off our discussion of bonding. So up to this point, we have talked about ionic bonds. And what types of things are involved in ionic bonds? What's that? Did somebody say ions? Because that's perfect. But specifically a cation with an anion. Okay? And then we talked about covalent bonds. And those form when electrons are shared between anions. Things that tend to become anions, but we already said they don't become ions when they share electrons, but they tend to become anions if they're in the vicinity of something that wants to get rid of electrons. If they're not, they don't become anions. They just share electrons with other atoms that would become anions. Now we need to do, well, what if there are two things that tend to become cations? Okay? What if there are two things that tend to become cations? And so as we begin this, you're going to see a lot of familiar words on this slide because it's almost the identical slide to what we saw last week. And if you're like, wow, Dr. Engel, real original, just reuse that slide again, I understand that feeling. But it's for a purpose. It's for a purpose. It's like when you eat a great meal, you don't want to go the rest of your life never eating that meal again, and you don't complain about having it again. So don't complain about having the slide again. This is our great meal. Okay? So you need to remember that cations will form ionic bonds with anions. You need to remember this. But of course you will, because now this is probably the fourth time you've written this down from a slide. You also need to remember what every atom wants. And what is it that every atom wants? Someone? To have 8 electrons in its outermost energy level. Or another way to say this, to have 8 valence electrons. That is what every atom wants. And every atom can have it. Every atom can have it by forming one of 3 types of bonds. Ionic bonds, covalent bonds, or what we're going to talk about today. Every atom can have it. Also remember, you're like, wow, this is not pretty much identical. This is identical so far to the first slide we had last week. Which, when you see this, you're like, wow, this must be really important, Dr. Engel, that you gave us the exact same slide. It's not the exact same, it gets a little different at the end. If 2 atoms tend to form cations interact, this is unique. If 2 atoms that tend to form cations interact, they must share electrons. So another way to say this is a point that was on last week's slide. If these 2 atoms with low electronegativities interact, they must also share electron. These are the things. These are cations, right? The atoms that tend to form cations are atoms with low electronegativity. Go ahead and take a moment to write this down, and then we'll talk about why is this the case. Somebody remind me what electronegativity is. And yes, I know it's written on the slide. The ability to attract electrons. So why would an atom with a low electronegativity tend to become a cation? How do you become a cation? I don't know, but it sounds horrible. Now, how do you become a cation? You lose electrons. And if you're losing electrons, do you have a great ability to attract electrons to yourself? No, you have a great ability to repel electrons from you, right? You're losing electrons. Does that make sense? How do you be, it'd be the equivalent to like, if you, in order to become a cation, you've got to lose some friends. Well, if you're great at attracting people to yourself, it's very challenging to lose friends. Every day you get new friends. I don't even know what to do with all these friends. Have you ever had that problem? I have so many friends that I can't even talk to them all. I got to put them on a rotation. I'll talk to you on the 2nd of every month. That's all I got. That's all I got to give. This is not me. I'm talking about in the guise of somebody with lots of friends. Okay. Also, when they share electrons, they do not become ions. They do not become ions. But now, so last week, if they won't ionic bond, they may do what? Covalent bond. That's how we answered it last week. But those are for atoms that tend to become anions, anions. But for atoms that tend to become cations, they do not covalent bond. They may, this is how you should answer it, they may metallic bond. They may metallic bond. You're like, wow, that sounds incredible. See, when I was in high school, heavy metal was really, really popular. I don't think heavy metal is really, really popular anymore. I don't even listen to it anymore. And if old people like me don't listen to it, you know it's not popular, right? That doesn't make any sense. Old people should listen to it if it's not popular. Oh my goodness. So when I hear metallic bond, I think of some like really incredible heavy metal band that sings songs about chemistry. Because that would be a great heavy metal band. Okay, so I know this is pretty much the same slide, so I wanted to share you a story to see why I think this is so important for you to get basically the same thing. So there was a preacher. And this preacher delivered the sermon of his life. Just had everybody in the auditorium just on the edge of their seats, being just completely impacted as the Spirit moved in them as this preacher preached from the Word of God, right? Just incredible. Best sermon you'd ever heard in your whole life. You leave that Sunday, for the rest of the day, you're pretty impacted by it. By the time the week comes on, the distractions of life start to distract you from the truth. So you come to church the very next Sunday, you sit down, and the pastor preaches the exact same sermon. Word for word. All the illustrations the same. All of the illustrations the same. Even the same jokes. And you're like, man, that was so impactful the first time. It still got me a little bit. Still got me a little bit. Not enough to even get you thinking about it the rest of the day, and certainly not enough to get you thinking about it through the rest of the week. So you show up to church on Sunday again, and the preacher gets up and delivers the exact same sermon a third week in a row. And you're like, man, by now it's not even impacting me. You know, I'm like a metal shield and it's bouncing right off of me. And then somebody's like, man, I think we ought to tell the pastor that he's giving the same sermon every week. I don't know if he knows. So you go with him just for moral support. You don't want to say anything because it's awkward. And he says, Pastor, you've given the same sermon 3 weeks in a row? And he said, yeah, and I'll stop when it actually makes a change in your life and impacts you throughout the week. It's like, bam! It hurts. And that single sentence cuts you deeper than even the first time you heard it. And this is what I'm doing with this. So it may not have got you that first time you heard it, you were like, man, this is like mind-blowing. But then you left class and it didn't change the way you live your life. So I'm giving it to you again. And I'm just going to keep giving you this slide at the beginning of every... just give you this exact same slide at the beginning of every one of our classes until it changes your life. You become a great chemist. This slide we've also seen many times. And again, we're aiming for life change here, okay? And so, where are we going to find elements that tend to become cations? We're going to find them over here. Because here, this jumps up into the next energy level once you start putting electrons in here. So any atom that ends here, its last electrons in its electron configuration are going to be in one of these s orbitals. And that jumps to the next energy level. Meaning they have very few electrons in that outermost energy level. How many do they want? They want 8. How many do they have? 1 or 2. This far away from 8. And so it's very easy for them to find something willing to take those electrons and to get rid of them. And if you want to know the chemistry behind why it's easy, let me know and I will give you the chemistry. Get you a little bit of quantum mechanics. You'll leave it wondering, like, how can a cat be both alive and dead at the same time until it's observed. But it'll be fun. Okay? And so these, very easy for them to get rid of these extra electrons. And when they do, then their highest energy level, like let's say we're dealing with something like in 5s. So this would be, let's see, this is calcium. This is potassium. Right? Right here? And then so here, would this be barium? What is it? Rubidium? Is this barium? What's here? Strontium. Gosh, I should have known. But let's say we're dealing with rubidium here. It's got 1 electron in energy level 5. Just 1. And if it loses it, now its highest energy level that has electrons is no longer 5. What is it? It's 4. And its highest energy electrons are fully filling this 4th energy level. And it's content. It's super stoked. Has everything it wants. Do people say stoked anymore? Okay. See, it's funny because things circle back. It's like there are words that were cool when I was a teenager, and then like by the time I was in my mid-20s, nobody said them anymore, and now they're circling back. Makes life very confusing. Anyway, like 90s fashion too, circling back. Gosh, it's horrible. It's horrible the first time, but it's coming back. It's got a stranglehold on us. We just can't get enough. Can't get enough of 90s fashion. All right, sorry. So, barium's going to lose that electron, and now it's a cation. So this is a great example of something that tends to form cations, and something that's a great candidate for forming what type of bond? A metallic bond. Metallic bond. All right? So let's talk a little bit about metals. What is a metal? What is a metal? And so here's what I want you to do. I want you to take 60, maybe 90 seconds. And I want you to work with those around you, and I want you to come up with the best definition of a metal that you can. The best definition of a metal that you can. We've done this before, right? Of metal, yes? Okay. All right. I want you, don't use that one. I mean, you can go back and use it. You're like, that's pretty good the first time. Okay? But try to come up with something. If you can remember it, that's fine. If you can come up with something, that's fine as well. 60, maybe 90 seconds, depending on how these conversations are going. Starting now. You're all alone?
Yeah, I was thinking.
Hey, just a surprise. I mean, to ruin your surprise, I'm going to define it a completely different way this time. Because this is the best definition for today. You're like, how can something be the best for today but not for always? I've got a great analogy for that. It just came to me. Alrighty. What do we got? Somebody define a metal for me. An element that tends to form cations. That is a great way to define a metal. for some other day. It's a great way to define a metal for some other day, not for today. Today it's good, but it's not the best. And you're like, Dr. Engel, how can it be good one day? I mean, it's still good today, but how can it be the best one day and not the best today? I mean, it's the same way, you know, like eating a sandwich is great in the middle of the day when you need enough energy to get you to dinner. But eating a sandwich in the middle of the night, it's still good. But you should be sleeping. Right? It's not the best use of your time. Although, it could be, I'll tell you what, sandwiches taste better in the middle of the night. When your kids wake you up and you can't go back to sleep, and you're like, cold pizza and ice cream. Cold pizza as the spoon for your ice cream. Charles.
Metals are usually hard.
Metals are usually hard. Also a great way to define a metal, not the best way for today. I'm going to give you a definition that none of you were prepared for. It's beautiful. Listen to this. A metal is a solid material with conduction electrons. Conduction electrons. Did you have this? With conduction electrons?
We were saying how metals have great conduction.
Oh. Yeah. Yeah, there's a reason why we call these conduction electrons. Because they are great conductors of heat and electricity, but we'll get there in a moment. Okay? So a solid material with conduction electrons. And here's what these electrons are. So these electrons pool around all the atoms in the metal. So in ionic bonds, the electrons transferred from the cation to the anion, right? Oh, sorry, I need to let you write this. I got really excited. Go ahead, I'll be quiet. What I should do during these quiet moments is just whisper secret material that the recording picks up. I don't have anything that came to mind. Okay. So in ionic bonds, the electrons transfer from being from surrounding the atom of the or the nucleus of the atom that becomes the cation to hovering around the nucleus of the atom that is now an anion. The electrons actually transferred, right? They were hovering around the nucleus of one atom. They are now hovering around the nucleus of another atom. In covalent bonds, the electrons are shared between two atoms. And they're spending a little bit of time around the nucleus of one, a little bit of time around the nucleus of another. In a metal, you've got, and you'll see this in a minute, I should have put this right now, but you've got lots of atoms and the electrons are just pooled all around them. Almost like you're surrounded in this electron lake, except for it's not liquid. It's mostly empty space, but it's like, sort of like a lake, but nothing really like a lake. Okay? It's just this pool of electrons, and it's really cool. Now, typically what happens is each atom in that metal contributes one of these electrons. It might contribute two at times, but usually on average, every atom contributes one of these conductance electrons that are just pooled. They're pooled around all the atoms. They don't hover around any nucleus. Just kind of build this weird little electron pool or lake. Probably be better to call it a field, but I don't want you to think like an athletic field, because then you'll think about the Rams losing, and then you'll just be so sad about all these LA teams that get all the way to the championship and then lose to a Boston team. Gosh. I mean, what does Boston even have good about it?
Nothing.
I know. It's like Philadelphia's got Philly cheesesteaks, New York's got pizza. Boston, I mean, what does it even have? Chicago's got a deep dish pizza and Chicago dogs, right? A hot dog with some chili peppers. It's a nice pepper, whole sliced tomato on it. It's delicious. What does Boston have? Nothing. What's that?
Accents.
Accents, ridiculous accents, and really good sports teams. That's what they got. Now, these types of bonds form really or relatively stable compounds that can include millions of metal atoms. Are any of your parents from Boston? Are they going to be offended listening to this recording? I mean, if so, that's fine. Just prepare them for it. Like, my parents don't listen to these recordings. Is this some kind of a joke? I had a student once that her dad would listen to all of the classes. And then if she didn't understand something, he would rebuke her. He's like, Dr. Engel explained it so clearly. There's no reason you should not understand that. That was my dad. It's just like, there's no excuse for what you're doing right now. I learned so much. All right. Millions of atoms. So you can take, let's go back to rubidium. Rubidium, if it finds something that's going to tend to form an anion, it'll give its electron to that, and they'll form a nice little ionic compound. But if it's only surrounded by other rubidium atoms, millions of them will aggregate together, and they will pool their electrons to form millions of electrons, just forming this weird little electron lake. And you're like, wow, it's a lot of electrons. What are they doing? And they're doing the things electrons tend to do. Be really good at absorbing energy in the form of heat, electricity, whatever. And this is what makes metals such great conductors of heat and electricity, because they've got this massive pool of electrons. Just like your body, which makes you such a great conductor of heat and electricity. That's why when you step into a sauna, man, do you get warmed up real quickly, right? Or you step into a lightning bolt, man, do you get electrified really quickly. Like, how do you step into a lightning bolt? You know there's a place on Earth that gets hit by a lightning bolt every 6 seconds. I think it's in Argentina. Somewhere in South America, I think it's Argentina. It's up really high in elevation. And it's like it's just a lightning magnet. And on average, it gets hit by one lightning bolt every 6 seconds. That's cool stuff.
And we're wearing some lightning-proof clothes.
You do. Yeah, something with very little metal in it, right? Like something like rubber. Like rubber is just a really complex polymer built by a whole bunch of non-metal materials. It's a horrible conductor of electricity. But it has really great friction, so it works really nicely to make tires out of, and then doubles to make your car a very bad conductor of electricity if the road gets hit by lightning. Now, if the metal part of your car gets hit by lightning, it's another story. But anyways, so what is a metal? Just answer this. C, S-E-E, my first point. C, my first point. This is going to be really random. Do any of you happen to have a potato on you? Because this is serious. I need a potato. I need a potato for my lab that starts 10 minutes after this class. I forgot to grab one. Nobody has a potato? Dang. You know, if you plug your nose and close your eyes and you bite into a potato, it's just like an apple. Just like an apple. But if you have your eyes open, you see that it's a potato. Because you can even know it's a potato, but if you close your eyes, it tricks your brain into thinking, I don't know what it is. And if you close your nose, you can't smell it. And then it's like biting into an apple. You can do that with an onion as well. Although the onion, when you bite into it, it'll release that gas. That then as soon as you open your eyes, you'll start crying. You know? Like I bit into this, oh, this isn't an apple. And then you're just so sad about it. All right. What are the properties of metals? Because this is all fine and good, right? We're like, oh, cool. Metals, they're made up of things that tend to form cations, but they can't because they don't have anything to take their electrons. So they're just going to pool them to get sort of 8 electrons around them. Right? It's like they've got 8 electrons hovering around the nucleus in the highest energy level, and the rest of the electrons are just pooled in this weird electron soup. That is a great That one is way better than a pool or a lake, an electron soup. You're like, is it delicious? Depends on the metal. All right, so some of the properties of metals. Metals have luster. It's a fancy chemistry way of saying that they are shiny. Metals have luster. Again, fancy way of saying that they are shiny. And a lot of this is because they reflect light. And part of that has to do with this the soup of electrons. I went back to pool, but the soup of electrons. And you're like, this is so cool. It's so cool. Metals are ductile. Metals are ductile, which of course means that ducks love them. It's not what it means at all. Metals are ductile. What that means is you can pull metals out into a thread or into a wire. Metals are ductile. You can pull them out into a wire.
So copper's a metal?
Copper is a metal. You bet it is. It's a great metal. It is actually pretty delicious, that soup of electrons around copper. You know, here's what's funny. You have several metals. You're like, nothing you say is funny. No, this one is funny. You have several metals that your body needs to carry out very specific reactions. You don't need a lot of it, but you need it to carry out very specific reactions. When your body is deficient in that metal, you crave that metal. And so if you were to taste the soup of that metal, it would taste good to you if you were deficient in that metal. So if you were deficient in copper, copper would taste good to you. If you're deficient in iron, iron tastes good to you. And you know where a great source of iron is? What's that? Red meat. Yeah, that's true. A lot of that hemoglobin, but also soil. And so sometimes when people are super, super iron deficient and you walk out and it's raining and you smell that and it's appetizing to you, it's because you're iron deficient. You can smell that iron in the soil and your body wants it. Anyways, that's another story. So ductile can be pulled into a wire. Metals are malleable. Metals are malleable. This adjective, you know what this means. You may have to think about it for a minute, but you know what this one means. These are great sentences, right? Just 3 words, you can write them real quick. What does it mean to be malleable? Yeah, Alex.
Can be shaped.
Yeah, it can be shaped, right? You all know this because you've heard some illustration about the need for you to be malleable, right? You need to be shaped so that the potter can shape you into something beautiful and not into some vessel for waste, right? Which is so fun when Paul's like, listen, some vessels are made to like show off and some vessels are made to put waste in. And he's using that as an analogy of people with their spiritual gifts and serving in the church. You're like, ooh, man. But then you realize it's still important, right? Of course, I mean, you use a toilet. But if before you could do that, they're all important. It's just some of them you just don't share with your friends. Right? Just like some people, their spiritual gifts. It's important. Just don't share it with your friends. Right? I don't know which spiritual gift Paul was talking about. All right. Metals typically have a really high melting point. So they tend to be solid at room temperature. There's one exception to that. They tend to be solid at room temperature. There's one exception. And I bet you all can, at least maybe some of you can think about it. But anyways, they tend to be solid at room temperature and you tend to have to heat them up a lot to get them to melt. What was it, Charles?
Mercury.
Mercury. Well done, Charles. It's beautiful. Yeah, mercury is liquid at room temperature, but it is absolutely a metal. And then these next two, we've already mentioned these. Metals are great conductors of heat. And again, that has to do with those conductance electrons. Electrons are really good at absorbing energy. So metals are great conductors of heat. It's why you like when you're eating like a really hot soup, You usually don't put it in a metal bowl. Put it in like a porcelain bowl or something that's not as good a conductor of heat, because otherwise you can't even touch it. You're like, I can't even carry this to the table, how am I going to eat it? And you're just like, I'll just eat it right here. Just serve the soup right up on the counter and just eat right there. You know what the best part about eating there standing up is? You don't have to go sit at the table with your family. Gosh, that was horrible, and it's recorded. I'm just kidding. I'm just kidding. I'm just kidding. I love to sit at the table and eat dinner with my family. Dinner's hard. Lunch, I love to eat lunch with my kids. The end of the day, little kids, those meals are hard. Like, they're just hard. Anyways, sorry. Metals are good conductors of electricity. Again, electrons are electricity. It's no coincidence that they start with the same 8 letters. Oh, they don't. Dang it. They start with the same 6 letters, because then it's R-O, it's O-N. Dang. But it's no coincidence that they start with the same 6 letters. Is that 6? 1, 2, 3, 4, 5, 6. Yes. Okay. Electrons are electricity. So of course, if you've got this massive soup of electrons just saturating these metal atoms, it makes sense why these are going to be great conductors of electricity. Okay. One more characteristic or property of metal. Metals will usually react with oxygen to corrode or rust. To corrode or rust. Oxygen is terrible for metals. Unless, of course, you want your metal to corrode. You know, copper, when it corrodes, it turns like a greenish blue, and it's actually really pretty. So, sometimes you want your metal to corrode. Build a nice little like copper accent wall in your backyard, and then over time it patinas. Have you heard that term? It's just a fancy way of saying corrodes. Corrode's the chemistry term. Patina's the art term. But yeah, it turns like a greenish blue. It's really pretty. Anyways. All right, so what are the properties of metals? How should we answer this question? C-list. C-list. Of course, S-E-E space L-I-S-T, not the letter C. Although that's pretty quick, right? C and then list, getting all technical with it. Making it to where nobody over the age of 20 can understand what you're saying. Love it. Okay, we have one more question to deal with. And then I've got another periodic table for you, but it's not the same one we usually see. It's new. It's new. So the last slide, what types of metals are there? What types of metals are there? Well, I'm glad you asked. Some of these we've seen before. Some of them, you've seen all of them before. But some of them we haven't talked about before. So I want you to take, about 60 seconds, maybe 90, depending on how the conversations are going. The last time we stopped at 60 because y'all weren't really talking all that much. And I want you to come up with types of metals, not like a specific element. So not like aluminum or gold or copper or silver. Those are all specific elements, but like maybe a category of metals. Some of these, again, we've talked about before. Some of them we haven't. So I'll give you 60 seconds starting now. Ooh. So nobody has a potato? No. Yeah.
What about even more specific? Like potassium, calcium. sodium, things you don't need. No? It's not. Where's it?
I'm not talking about that. I had to find a potato. Okay, so what do we got? What are some metals? We didn't get anywhere? Oh, some of these you've seen before. You're going to be disappointed in yourself. The first column on the periodic table, known as the alkali metals. Saw that just before we went on break. Ooh. Just before we went on break. And these metals, when they form cations, how many electrons do they lose? One. Like rubidium, or potassium, or sodium even, or lithium. Lithium ion batteries. It's good stuff. Now, do you know any others? Transition metals. We're not quite there yet. That's my third point. The alkaline earth metals in the second column on the periodic table. The alkaline earth metals. And so when these form cations, how many electrons do they lose? 2, like calcium and magnesium. And what did you all say? Strontium? Was that what was next to rubidium? Barium next to lithium. Oh, why did I think barium was... Where's barium?
6.
Oh, 6. What's right next to... Beryllium is right next to lithium. Gosh, y'all deserve better than that. I know better than that. It's embarrassing. And it was recorded. Columns 3 through 12. These are the transition metals. Columns 3 through 12. These are the transition metals. And these are metals that are starting to not behave so metal-like. They maybe aren't as good conductors of electricity as the alkali and the alkaline earth metals. Or they aren't as good of conductors of heat. Maybe aren't as reactive with oxygen. Okay. But they're very clearly metals. Okay? Very clearly metals. Now, columns 13 through 16. Now you start to get something really interesting happening. In columns 13 through 16, we have both metalloids and nonmetals. Metalloids. What on earth is that? Metalloids, also known as poor metals, not because they lack the financial resources necessary to make it through life, but because they don't have many of the features of metals, and they start to have some features of nonmetals. They tend to be poor conductors of heat and electricity. They tend to not be malleable and ductile. Tend to not have an impressive luster and have instead more of a dull appearance. Okay. The key is, and you're like, well, how do we know? How do we know which ones in that column are metalloids and which are nonmetals? It's an excellent question. You look for the black staircase. You look for the black staircase. This is why I have to show you a new periodic table, because yours doesn't have a black staircase, does it? Is there a black staircase on yours? And then the one that I've shown you on the slides many, many times also lacks a black staircase. And so I'm going to show you a periodic table that has this black staircase in place. But first, we need to answer our question. What types of metals are there? C-list. I think that is a wonderful way to answer that question, Charles. And you're killing it. The mercury, answering that question.
knowing when you were already giving us the answers. So
So, you're exactly right. All right, any questions about this question? All right, so here's the periodic table. And you look for the black staircase. Where's the black staircase? It's right here. Everything to the right of this black staircase is a non-metal. Meaning it is dull in appearance. It tends to have a low melting point. It is not ductile. It's not malleable. It's not a good conductor of heat. It's not a good conductor of electricity. What was that? Oh, it doesn't, when it reacts with oxygen, it's not going to rust or corrode. Everything to the left of this, but still over here, is a poor metal or a metalloid. And again, we don't call it a poor metal because we feel sorry for it. We just literally mean it's a poor metal. Like some things are just poor excuses for food, right? Like kale. Or quinoa. Oh, flaxseed, right? You all know what flaxseed is? If you like flaxseed, that's great. But you know what flaxseed looks like? I mean, spot on. It looks like a gravid louse. Head lice. You look at a gravid female louse that's just packed full of eggs and she's taking a huge blood meal to make those eggs. Man, that's what a flaxseed looks like. And I hope I've ruined flaxseed for you. I mean, if it already didn't ruin itself for you, I hope I've tipped the scales. I mean, flaxseed is fine. Eat all the flaxseed you want. Eat all the quinoa you want. But you have to admit, man, this is a poor excuse for food, right? But it's what's the term? Non-processed grains. I mean, they're great sources of sugar. They are not delicious. They are not delicious. We need those processed grains, right? Those things that just have way too many calories per unit mass because they've been super processed. That's what you need if you want something delicious, right? If you want to make a pizza so you can have that cold pizza ice cream combo, you got to take wheat that's like super glutenated, and then you've got to add gluten to the flour too. You know, like a little bit of gluten, that's not enough. We need extra gluten. You know why? Because gluten's sticky and delicious. I mean, you know, gives you a leaky gut, but you know, so be it. So be it. All right. Any questions? Thoughts? Concerns? Okay. All right. That's it. I gotta go find my tater.